All right, so hi everyone. This is a joint work with Alex Braun, who's in the audience, Thomas Kesselheim, and my advisor, Amin Saberi. So at a high level, the question that we're interested in is how do we assign resources online to agents in a way that maximizes social welfare? And I'm going to jump right in and say what's the problem statement. So we imagine that there's a weighted bipartite graph with one side consisting of offline agents and one side consisting of online resources. In this case, I've denoted them by these cars that arrive in some known order. And what makes this problem challenging is that the arrivals need to be determined online and are stochastic. So in particular, each resource T arrives only with some probability P sub T and has some capacity C sub T that's only going to fit some number of the offline agents. And as soon as this, if this like car does arrive, we need to decide immediately and irrevocably how to, assign it to at most CT users. So as an example, in this case, the first car arriving with probability half. So maybe, and also I want to emphasize in this work, we consider a slightly more general arrival model, but the main intuition is captured by this case where they only show up with some probability. So maybe, if we're running it on this instance, the first car does show up with probability half, and then we have some decision, which of these two agents do we match it to? Maybe we match it to the first one and generate reward 3. Maybe in this input, the second arrival does not show up. So there's no decision to make because it only was going to come with probability 0.2. And the third arrival does show up with probability half. It has capacity 2. So we can match the remaining 2 offline agents and generate this true word. So are there any questions about the problem statement?
Does the online algorithm know the cars, like their capacity?
Yeah, so the online algorithm knows the order, all the capacities, it knows everything except for the actual realization of those arrival. Good, so there's some prior work on this problem. It's been studied from the perspective of profit inequalities. So in particular, there are a couple of algorithms known that are half competitive, meaning they get a half approximation to this profit benchmark that sees all of the arrivals at once and then can just pick the best allocation in the resulting graph. And yeah, this is like a very sort of like, I would say, dominant paradigm of analyzing online algorithms. It's part of like a very large literature that's important to the EC community. And many sorts of feasibility constraints are considered. So one fact too is like by a standard example in this problem I just mentioned, you cannot get better than 1/2 against this profit benchmark. And we might ask, okay, based on that, are we done? Is there anything else interesting to say about this problem? So one point I want to make is that when we design algorithms that are optimal against the profit benchmark, it doesn't necessarily mean that they perform amazing in practice. So I have this really simple toy example where there's an agent adjacent to 2 cars arriving with probability 1, and the weights on the edges are 1 and 2. So clearly you want to wait for the second car and generate reward 2. Surprisingly, existing algorithms might match the first edge because it's still getting half of the profit benchmark. But it suggests that maybe there's more to be done for this problem. So in some sense, like to make some progress, the issue is that this profit with his crystal ball that can look into the future is too strong. So we consider a different benchmark. So in particular, we considered the benchmark of the optimal online algorithm, which sort of breaks this like crystal ball. It's formed by just like solving the Bellman equation using some sort of backwards induction to compute the exactly optimal online policy. So we just heard about this in the previous talk, and the main sort of difference is that in this case, if you try to like think about this optimal online policy, it's going to require exponential time because the number of states is going to be exponential in the number of offline nodes. So, as we mentioned, this is like a somewhat new direction, but it has already seen a bit of research. And one of the most fundamental questions we can ask is how do polynomial time algorithms compare to this benchmark? I want to emphasize that you can also ask other interesting questions about this benchmark. You can look at order unaware algorithms, as we just saw, or thresholding algorithms. But in the case where the optimum online might take a long time, the most fundamental thing we could ask is maybe how do we compare it if we need to be efficient? And because this benchmark, in some sense has a lot of time to compute, but can't see into the future, we think that a reasonable name for it could be something like a philosopher, because at each time step, it has a long, long time to think about what is the optimal thing to do. And, but it can't see into the future at all. So this problem that I've mentioned, in the case where the arriving resources all have unit capacities, and when it's an online matching problem, is have been pretty, there's a line of work studying this problem. We know that it's p-space hard to approximate it within some constant factor, and there's sort of been a line of work improving the approximation ratio. But it was unknown, what can you do if the capacities are not all one? So in this work, our main result is to give an online algorithm that beats half against the online benchmark in the case of general capacities. And it results in some corollaries that I don't have time to get into today, but the results extend to more general arrivals with more general rewards, and we can also turn them into some dominant strategy incentive compatible mechanisms. So if you're interested about that, you can ask me after. And before getting into the details of how we do this, I want to emphasize what is the technical contribution of this work. And in this case, it's handling positive correlation among the agents. So I just want to give some intuition for why this is so important. I have this really toy example where we have two agents, I and J. There's some car with capacity 1 that arrives with probability P. The weights are the same. So, anything is optimal here. For example, one optimal algorithm would be to match this car uniformly at random if it shows up. So notice the probability I match I is the same as the probability I match J. It's just P over 2 if this car is arriving with probability P. And the probability I match both of them is 0. So it's very simple, but it shows that there's negative correlation between these agents. And in fact, all the algorithms that are designed for this unit capacity case achieve this sort of negative correlation among offline agents, because you only need to match one of them at a time. So in contrast, if you look at the case of general capacity resources, for example, a car with a capacity 2 here, if you want to be optimal, each of them gets matched individually with probability P, but also there's a P chance that you match both of them. So there's like a strong positive correlation. And in fact, so you might say this is a little strong because we're thinking about designing approximation algorithms, not optimal algorithms. But in fact, imagine you'd want to do some approximation algorithm that beats 1/2. So what you need is that the sum of these individual probabilities should be at least 0.51 times the opt of 2p. But observe, each of the individual marginals is at most p. So the product of the probability match I and the probability match J is at most p squared. Now the point is, the probability you can match either I or J is at most p, because that's the chance this car arrives with. So if the sum of these probabilities is more than p, there's going to be something in the intersection, right? So in particular, the bound, if you do the calculation, the chance that, that both happen is going to be at least, in this case, 0.02 times p. So notice if I take p very small, it's definitely going to have some form of positive correlation. And interestingly, half is exactly the threshold where you need to have some positive correlation in order to say something for general capacities. So this brings me to what I view as kind of the conceptual contribution of this work. So when we think about what was known for this problem from the profit inequality standpoint, you can get 1/2 for unit capacities. You can get 1/2 for general capacities. You can even go beyond that to more general problems and get 1/2. And they all these problems look the same. The same algorithm can give a 1/2 approximation to the profit, and you actually don't need to care at all about the correlation introduced in the offline node. So I've kind of represented this by the profit, the way I think of it is the profit is such a strong benchmark. It's so far away from all of us on Earth that to it, this tiny smart car and this larger capacity car, it can't really tell the difference. It's so it's just such a strong benchmark. Whereas when we started this project and we competed with the Optimum Online or the Philosopher benchmark, we realized that these are actually quite different problems. And in fact, if you want to get a better than 1/2 approximation, or really just like design a good algorithm for this problem, it's really crucial to think about how do you correlate the agents as the arrivals show up. So we think this is an interesting conceptual contribution that, competing with this new benchmark can reveal some problem-specific differences that are not relevant to the standard competitive analysis. So now I'll briefly mention how do we design this algorithm to beat 1/2. So we use the same LP relaxation from prior work. So the notation reminder, online node T has capacity CT and arrival probability PT. The weights on the edges are denoted by WIT. So, and in this LP, you should think of XIT as being the probability that the algorithm matches I to T. So these first two constraints are natural, and they actually also hold for the profit benchmark. The first one is saying that the condition on T arriving, the number of things you can match to an arrival T is at most its capacity. The second constraint is saying that you can match an expectation each offline node at most. The third thing is something that only holds for online algorithms. What we're saying here is that the probability you match I to T is at most the probability T actually shows up times 1 minus the LP's fractional degree at T, which is the sum over all T prime less than T of XIT prime. So that term, the 1 minus the fractional degree, that's exactly the probability that I is free under the LP. And for an online algorithm, the chance I match I to T, the chance that I is free just before T arrives, and the chance that T does actually show up are totally independent events. That's why we can multiply them and have this LP constraint. If I have an offline algorithm, what I choose to do at time T could well depend on future arrivals, and this constraint would not be true. So, I want to briefly, our work builds on like the known algorithms that get 1/2 approximations to the profit. So I want to show you one simple such algorithm. So for each T, if it arrives, what we're going to do is propose to at most CT, at most the capacity number of offline nodes, such that each I is proposed to with probability XIT over PT. So XIT over PT are some numbers that sum to at most the capacity CT. And we can do this step with a black box use of a known algorithm called pivotal sampling. The details are not important for this talk, so you can just think of this as a black box call that has that property. And then if I is free and got a proposal, we match the T with this red probability, which is 1/2 over 1 minus 1/2 times the fractional degree. So if you haven't seen this before and you're wondering where does this red term come from, you'll see in 10 seconds. So the claim is that this algorithm matches each edge IT with probability exactly 1/2 of what the LP tells you. So notice to do the calculation, we'll do it by induction on T. For an edge IT to be matched, first of all, T should show up, which happens with probability PT. I should be free when T arrives. It needs to get a proposal, which is this blue number, and it needs to accept the proposal, which is this red number. Now, by induction on T, we can simplify this probability that I is free when T arrives. So in particular, it's 1 minus the chance it was matched to some earlier one. Subbing in the probabilities of those events, we have that it's 1 minus 1/2 times the fractional degree. So if you look, it's just a big cancellation, and what I get is 1/2 XIT. Okay, so one other observation we can make is that the most naive thing we might try to do to boost the approximation ratio is make this red number bigger. And we notice that if the fractional degree is significantly smaller than 1, we actually can change this 1/2 to a larger, like 0.51, let's say, and there are going to be no issues with analyzing this algorithm. The challenge is when the fractional degree is close to 1, this boosting trick is not going to work because that red probability is already around 1. So I'm going to just for simplicity talk about how could we do this, how could we improve on this 1/2 factor for the final arrival. So this is the same algorithm that I presented before. I've only changed the red acceptance probability to have a 0.51, the boosted version. And I put the min of 1 in case that second number is not actually a probability that's smaller than 1. Good. So now, just for the final arrival, here's the idea we're going to use to, improve on the half algorithm that we currently have. We're going to let FPT be the number of offline nodes that T got in the first proposal. And we're going to hope that sometimes it was the case that this number FPT is smaller than CT, because that means that, there's actually some remaining capacity in the arrival to serve more agents. So in particular, we'll propose to some number of nodes that is exactly at most the remaining capacity, which is the CT minus FPT. So we do the same black box call to the pivotal sampling algorithm with these marginals, CT minus FPT times XIT over PT. And yeah, so the analysis techniques that we use here are, we're going to just pick some offline node I, and we'll imagine that this fractional degree is close to 1. Because remember, if that fractional degree was significantly below 1, then already this red expression is going to provide the boost that we need. The 0.51 instead of the 0.5 will be enough. So we imagine that its fractional degree is close to 1. We let FIT be an indicator for the event that I is free when T arrives. And we observe that its probability is approximately 1/2. So recall the chance it gets a proposal in the first round is XIT over PT. And now here's like one of our insights. We actually have an upper bound on this from the LP. So in particular, it holds for online algorithms that XIT over PT is at most 1 minus the fractional degree. So when the fractional degree is large, this XIT over PT is very small. So that means that it's a very low chance I gets a proposal from T in the first round. And this is actually going to help us because that's going to mean it's more likely to actually get a boost from the second round of proposals, which is what we're trying to analyze. So in particular, the chance that IT is matched in the second try, it's approximately lower bounded by the following. T should arrive, so that happens with probability PT. I should be free when T arrives, so it happens with probability FIT. And now, here's why the light bulb is a useful insight. There's no worries that maybe it's already occupied from the first proposal because it probably didn't get one. So roughly, we can say that the chance it gets matched is just the marginal probability that the second algorithm puts on it, that the second proposal puts on it. So it's like this remaining capacity times the LP's value of XIT over PT. But there is one challenge in analyzing this, and it's the fact that we condition on, FIT. So in particular, the main hurdle that we have to overcome is if these offline nodes are very positively correlated, there could be some major problems. So let me explain why. So in the second line here, I just simplified just did some algebra, canceled out the PTs and moved the XIT to the front. In this expectation, we're just looking at the expected remaining capacity after the first proposal. So CT, the capacity minus the number of things it matched in the first proposal. So imagine that when I condition on FIT, it's like conditioning on everyone else being free as well. Then the issue is this first proposal, they could all accept with probability 1, and there would sort of be no room left to do anything in the second proposal. So the main technical contribution that we give here is that we bound the correlation, the positive correlation that is introduced throughout the algorithm. It's essential that there is some, but we use the fact that the randomness in the accepting, the accepting of proposals is independent of the online analysis. And because of that independence, we can argue that we avoid this extreme positive correlation, and hence this sort of a second proposal step can do something. So, great, so wrapping up, so we gave a polynomial time 0.51 approximation to optimum online for this problem of online capacitated allocation. Well, we have some extensions to general arrival distributions and more complicated rewards and some mechanism design considerations. What we find interesting about this is that looking at the online benchmark instead of just the offline benchmark led us to some problem-specific insights about how capacities affect the design of algorithms and mechanisms in that space. And I hope that that's what you can take away from this talk. So it suggests some natural future questions. We might wonder, how can we improve the approximation ratio? And there might be some other questions where optimum online is an interesting benchmark. It's a very sort of like dominant paradigm to look at profit inequality perspective. And there are perhaps other questions where a similar, approach could be. So yeah, thanks very much. I'm happy to take questions.